So here's the good news about chapter 5. We want the bad news first. Bad news? It's more probability.
Well, good news is.
Okay, the good news is I think it's actually easier than what we did in chapter 4. So that's why I said maybe we should do the bad news first. It is more probability, but it's what's nice about chapter 5 is it follows a very clear, strict process, and that there's not a lot of all this different rules you have to keep in your head, like the at least ones where you have to know the complements and maybe complements twice and the multiplication rule all combined together. So it's a little bit more straightforward as long as you understand the terminology. So I'm looking at the top of page 56. There's this chart there, which is my first example. We can read up above there, but it may not make sense. Let's try to read it and then we'll look at this example and tie those together. So it's all about what we call probability distributions. Sounds all fancy. A probability distribution, here's my words, is a list where you have some numbers here of all the things that could happen. And then you have the probabilities next to them of how likely that is to happen. We'll go back to the definition in a second. So my first example is if a family has 4 children, and X was the number of girls, it's listed on there. If a family has 4 kids, what are all the possible number of girls they could have? Maybe they have no girls. Maybe they have 1 girl. Maybe they have 2 or 3. These are the only things that might happen. If you ask a family of 4, how many girls do you have? Do you agree these are all the possible answers? And then next to these are the probability of each one of those particular things happening. For example, the probability of no girls in a family of 4. Here's a little review question for you. How would you find the probability of no girls in a family of 4? Yes?
1/2 to the power of 4.
1/2. So the first one's not a girl, the second one's not a girl, and the third one's not a girl, and the fourth one's not a girl. That actually is where that number comes from. Another way you could think about this is we could have made the sample space for a family of 4 kids. The sample space member maybe would be all girls. Oops, only 4 kids. Only 4. I'll have to put a 5th one on there. All girls. Maybe the first 3 were girls and then there was a boy. Or maybe there were 2 girls and then a boy and then a girl. And if we listed all of these, how many things would be in this sample space? How many outcomes are possible? 16. Why? Because that's the denominator, but every time there's 1 child, there's 2 possibilities for the first child, 2 for the next, 2 for the next, and 2 for the next. So those multiply out to be 16. So we could list all 16 of those. And only 1 of those 16, if I wanted to list them all, would have no girls. What would it look like, the one that has no girls?
All boys.
All boys, right? So that one would be over here, maybe be my last one, if I was doing them in order. There's 16 of these. Maybe this one is the one, there's the only one there that has no girls in it. And then maybe we'd go through and say, okay, well, how many of those have exactly 1 girl? And we'd have to count. We did these with 3 kids on the lab assignment last time, actually. It was like 3 out of 8 had exactly 1 girl or something like that. Everyone okay with where we could find all these numbers if you wanted to? List your sample space and count them. So somebody just organized all the possibilities for us in one place. I'm not going to ask you to necessarily create the whole distribution. There'll be times when we do. But you want to just understand that these are all the things that could happen, and this is the probability for each. Okay there? So let's go back up to the definition. It's a description that gives the probability of 4. That's good English. The probability for each value of x, usually in a table, sometimes in a graph. We'll look at graphs later. Probability distributions are very similar to relative frequency distributions. You guys remember those from way back when in chapter, I think it might have been 2. Might have been 1. I think it was chapter 2. What was the relative frequency distribution?
Percentage.
Where you had to turn your counts into percents. Well, if you change percents into decimals, now they're probabilities, right? So it's very similar to the relative that we did before. Here I left them as fractions, but you agree we could turn those all into decimals or percents if we wanted? Then it'd be like a relative frequency distribution. The random variable is up above there. That's the x. This has to be a number. We did some charts like this where you had categories, you know, favorite candies, Skittles, M&Ms, whatever. Those are not numbers. I know you could count how many people like Skittles or M&Ms, but the values over here have to be a random variable that is a number. The very first few questions on your lab assignment or your online assignment say, is this a probability distribution? And if these aren't numbers, the answer is no. Don't even worry about anything else. So your random variable is some number. How many of something might happen? In this case, it's how many girls might happen. Underneath example 6, random variables can be discrete or continuous. So there's some more review words. What are those? Discrete or continuous.
Countable,
Countable is discrete, I like that.
and then there's a decimal and the continuous.
Continuous answers could be decimals. So if I say there's a family with 4 children, could the number of girls be a decimal? I have 3.8 girls. That wouldn't be able to happen. So in this case, this is a discrete example. But if I said, you know, how tall are you? You could tell me that you're 5.5 feet tall, and a fraction would make sense there. So that's what we mean. It could be discrete or continuous. This example is discrete. And then there's these probability requirements, which look scary, but we're going to interpret them. Requirements to be a probability distribution. Here's the first requirement. Somebody tell me what that means in English.
It means sums.
Okay, she says this means sum.
And
PX would be
the probability.
the probabilities, right? Those are all the probabilities. So let's just go with what Kirsty's telling us, right? She says this means sum, and this means probabilities. So somebody tell me an English sentence that this says. Hang on, Kirsty, I know you're all over it. I want to see somebody else got it. Yes, baby.
The sum of the probabilities has to equal 1.
The sum of the probabilities has to equal 1. Equal 1. Everyone agree that's what it says? Yes, Kirsty?
I have a quick question about something you said about the random variables.
Yes.
You said that they weren't numbers?
They have to be
Oh,
numbers.
they have to.
So I said, for example, if I asked you what your favorite kind of candy was, like we had charts like this with, you know, different categories of candy and people who liked each one. Those would not be random variables because Skittles is not a number. And M&M's.
So they have to be quantitative?
Yes, has to be quantitative. So there's, I know for sure there's one problem on the lab where the directions say, is this a probability distribution? If so, then they ask a follow-up question. But if there's categories here as opposed to numbers, the answer is no, it's not a probability distribution. Thank you for clarifying. We okay on that statement? What does that mean? Why does this make sense? They have to add up to 1.
Well, it's like this percentage, how when we did that with the other one. we
The
did,
relative frequency,
It all
yeah?
had to add up to 100%.
Okay, do you remember when we did relative frequencies, which was months ago now, it feels like, that all of the percentages had up to 100%? Because everybody had to be accounted for? So 100%, when you change it to a decimal, is just the number 1. If we add up all these fractions, what should they add up to? 1. The reason they add up to 1 is because if a family has 4 kids, do they either have 0, 1, or 2, or 3, or 4 girls? All of them with an or? They either have 0 girls, or 1 girl, or 2 girls, or 3 girls, or 4 girls. Sorry, what did you say?
They have 4.
They could have 4, but they might only have 2 girls. But they must have one of these things. If they either have this, or this, or this, or it's guaranteed that they have one of these options. And if something is guaranteed, it's certain, the total probability is 1. So the total here equals 1. To verify that, we would have to get a common denominator, add them all up. Let's do that real quick. This is already out of 16. This is 4 out of 16. I'm multiplying by whatever I need to, oops, I made 18 there. Multiplying by whatever I need to get a common denominator. Like I multiply this one by 4 over 4, this one by 2 over 2. What do those all add up to? Please tell me it's 16, right? 16 over 16?
Which equals 1.
Which equals 1. If it didn't equal 1, imagine if I said, hey, there's a 20% chance it's going to rain today, and a 50% chance it won't rain today. Some of you are laughing, which is a good sign for me. Let me say it again. There's a 20% chance it will rain, and a 50% chance it won't rain. What's wrong with that statement?
Where's the other 30%?
There's another 30% that's missing somewhere, right? And the only options are it rains or it doesn't rain, so where's the other 30%? That you can't not add up to 100% chance, right? So the same thing, your probabilities can't not add up to 1. That means there's something else that could happen. They always have to add up to 1. So that's the first requirement. They have to add up to 1. And then what's the number 2 statement say? This one. How do you interpret this? It looks scarier than it is.
Or bigger than 0.
Say it again, Kirsty, I couldn't hear you.
It has to be equal to or bigger than 0, or equal to or lesser than 1.
Okay, so this says something, you didn't tell me what. Something has to be equal or bigger than 0 and less than or equal to 1.
Oh, the probability.
The probability. This is the probability. Try to put this in some other nicer words for us. English, with less math. Let's just tell you about your probabilities.
You have to be between 0 and 1.
Greater than 0 and less than 1, she says. What did you say, Kevin?
This is between 0 and 1.
Has to be between 0 and 1, which is what we learned on day 1 of probabilities, right? This is nothing new, it's just the format looks scary because of the notation. This says probabilities have to be between 0 and 1. We already knew that. Must, I can't spell today. So if over here I had, you know, a 1.8 in my table, that's bigger than 1. That can't be a probability. That would automatically make it not a probability distribution. So they have to be probabilities. That's really what this says. Numbers between 0 and 1. And they have to add up to 1. So we agree that this one is a probability distribution. They add up to 1. We check that. Each one is a fraction that's between 0 and 1. So that's a probability distribution. Now, we quite often ask for the mean of this probability distribution. The mean. In this case, it's the number of girls. If a family has 4 kids, on average, how many girls do you think they have? 2, he says. If there's 4 kids, you would expect that 2 of them would be girls. Now, I know it's not a guarantee, but on average, do we agree that out of 4 kids, 2 would be girls? Some people have more, some people have less, but if you average them, does that make sense? That's what we mean when we ask about the mean of the distribution. So the mean of the distribution here is what's the mean number of girls that we could expect. Here's the deal though. You can't just add all these numbers up and divide by however many you have. It works in this case because of the very specific nature of boys and girls being equally likely. But imagine if it was winning the lottery. You win or you lose. Sometimes you win $1 million and sometimes you lose $1. On average, you don't just say that on average we all win $500,000. Right? I mean, it doesn't work that way. Because why not? Why can't we just average those 2 numbers?
Too many variables.
You might win $1 million. Let's write this out. Too many variables. What do you mean by too many variables?
Well, because you're taking into account what might happen and what will happen, and I don't know.
It's like leaving.
Yes.
So you either win $1 million or you lose your $1. We agree with that? And technically you don't win $1 million. You really only win $999,999 because you paid $1 to get in. I better change that. You really only win this much because you had to pay $1 to join, right? So you might win this or you might lose this. That's everything that might happen when you play the lottery. I know there's some other in-between prizes, but let's pretend there's not. If I average these 2 numbers, add them up, divide by 2, it's like $450-something thousand. On average, does everyone who plays get $450,000? I never met those people. Yeah, she wishes. So why can't I just add these up and divide by 2? What's the problem here? Yes?
Is it because you're taking into, like,
you can't win and lose the lottery, and that's,
Well, okay, I'm not saying I'm gonna do both, I'm just trying to average this, because those are two things that could happen. You could win or you could lose. So I'm trying to say on average, every time you play, what might happen. And some people are winning and some people are losing. If I add them up and divide by 2, I'm assuming something now, which is not true. Well, I'm not necessarily assuming I'll still get money. Let me ask you a question. Is this just as likely to happen as this?
No.
No, right? You're not just as likely to win this as you are. So they're not equally likely. If they're not equally likely, that's why we can't just add them up and divide by 2. Because for every one of these, how many of these are there? A whole bunch more, right? So there maybe might be one person that wins $1 million, and there's a whole bunch of us who lose $1. So we technically would have to consider all those people as well. So you can't just take those two possibilities. We have to consider the probabilities, which is we're actually going to do a similar example to this in a minute. Talk about how to calculate on average what happens. But that's what we do when we talk about the mean of the distribution. We also talk about the variance of the distribution, how far away you expect to be from the mean. We said the mean is 2. We're going to calculate here in a second how far away. And we can get the standard deviation. I agree that all 3 of those formulas are very scary. I'm not even going to try to interpret them for you because we're going to find all of this on our calculators. We love our calculators. So we have to go back and jog our memories on how to do all this. What I want to do is type this distribution into my calculator into list 1 and list 2. So we go to stat and edit. If my computer's on today. Stat and edit. Sounds like it is. Good. Let's jog our memories here.
what are we adding?
The table that we have here that was given to us, these numbers go into the list 1, and these, let me highlight it here, and the second ones go into list 2. So the x's go into list 1 and the probabilities go into list 2. Could you turn off one of those light switches behind you there, Nick?
You just
Thank you.
just add
Let's see if this
arrow.
comes on. So if you can see it. It came on. Oh, he's turned it off.
Comes up as a decimal.
Oh, here it comes. Give it a chance to start up. I want to make sure everyone sees the subtle difference because depending on which calculator you have, how you get there, it looks a little bit different. We have to wait patiently. Does everyone remember how to please type them into their lists? And by the way, you can just type these in right as fractions, and your calculator will turn them into decimals as you do it.
Yeah. So let's do it.
List 1 and list 2. Anyone need me to jog their memory on how to get to that page? So I'm going to go do that real quick here. So I'm going to go to stat, tell it I want to edit, and I have 0,
Then you go to calculate.
1, 2, 3, and 4. And then over here, I try to always use my mouse because I can't do it on here. 1 divided by 16. So I'm actually typing in 1 divided by 16 right here. But when I hit enter, it turns into a decimal, which is fine. My next one was 1/4. I'm going to put into a decimal right away because I know that one. The next one is 3/8. And then 1/4. And 1/16 again. So I have all those in there, list 1 and list 2. Again, just like we did before back in chapter 3, when you want the mean, we're going to use one of our stats. That hasn't changed. So we're going to go back into the stats button here. Stats. We're going to move over up here to where it says calculate. Remember that? It's been a while. We're going to be doing heavy calculator use pretty much every day from now on. One of our stats. Only hit enter once. Now if you have my calculator that looks like this, some of you don't, some of you have something else, so pause if you don't have this. If your calculator looks like this, we need to tell it that list 1 is my x's, which we already have there. You see where it says frequency list? we need to tell it to look at list 2. So I'm gonna come down here. List 2 is in blue down here above the number 2. So I have to hit the second and then the list 2. If you don't have this screen and all you have is a 1-bar stats typed on your screen, I can't show you yet what it'll look like. It's going to disappear. Some of you have the calculator that only just says 1-bar stats. It doesn't have this pretty screen. 1 second, Kirsty. Then you're going to type in L1, comma L2 right after that before you hit enter. Yes, Kirsty.
Oh, no, I was saying I have that one.
Oh, okay, if you have that one. Everyone know how to find the L1, the L2, and the comma? So you're either typing this, or your screen looks like mine up there. Everyone have one or the other?
What did you say? If you have the 1-bar stats, what do you have to type?
So once you have 1-bar stats showing on your screen, then you type L1, comma L2 before you hit enter. So right next to where it says 1-bar stats. Do you see how to get there?
Yeah.
Or not? Yeah? If you do this and then we go down to calculate, or the rest of us hit enter over here,
So it's just like formatted things. I was like that.
calculate, we get this. So I want to know if we can all get to this screen. Can you see that, Nick? Is it too big? We're good?
Yeah.
Anyone having trouble getting here?
I am.
You are having trouble?
I'm on calculate, and when I go down to various stats, I'm sure
So you have to hit enter to choose, that's the one you want. So hit enter once you're on that. And now right after that, you want to do L1, comma L2.
oh, after that.
Yes. You're welcome. Anybody else? Come over there, Christine.
No, my hair's never. We'll just say my hair's as long as it doesn't there's like maybe good hair. That was in the
Yeah.
fifth grade, since fifth grade. Just
L1 and then comma.
it's short. It will grow to like that one length and then yeah. So it could just say like the length it is right now is as long as it grows. Like I can cut like 2 inches out and then it'll just grow
Yes.
back that 2 inches and that's it.
I'll fix it later. Right now, just tell it that your frequency list is
I've
L3
taken it out, but
instead of
I need to
L2.
break
I'll
down
put it
some
back in
stuff.
a minute. It actually got deleted. So that's a good point. Her L2 got deleted accidentally. So you just tell your calculator, look at L1 and L3. I'll fix the L2 issue in a minute. But you can put in any list you want. Just tell it which list that you put them in. Did you get it with the L3? Okay. I'll fix your L2. Don't forget to tell me at the break to fix your L2. We have this screen now. Everyone's there? What does this tell us? What's that X bar tell us? The mean. Remember we already said we're pretty sure the mean is 2 here. Remember we said the average number of girls we thought would be 2? So the X bar is the mean. If I ask you to find the mean of a probability distribution, guess what you're going to do? Use your calculator and know how to read it off the screen. And again, on an exam, I will always tell you how to use the calculator. If you're telling me I can't find 1-bar stats, I'll help you find it. If you tell me I've got these 2 lists and I can't remember how to type that in, I will always help you with your calculator. So there's the X bar. What else is on this screen? Look at the SX is blank. See the SX is blank? I don't know if you recall, way back when in chapter 3, I said we're always going to use SX. SX is the one that we want when we're finding the standard deviation. And I said there's one exception when we won't use it. Today's the day. Guess why we're not using it? It's not there. Because SX is from the sample. And this probability distribution actually represents the entire population. This represents all possible families of size 4. There's nobody left out here. It's all the possibilities. So instead of SX, we're going to look at sigma x. What is sigma? I hear some people quietly saying it. Somebody confident enough to say it? Louder? I hear everybody whispering. The circle thing, yeah, it looks like this, but what does it represent? The population, standard deviation, thank you, teamwork, we like it. That's the population standard deviation. Which in this case is 1. Now, our calculators gave us x bar equals 2. But look at what our formula is asking for. The mean has a mu in front of it. You see that on the formula in the middle of page 56? It's supposed to be a mu. What is mu? Population mean. So that's the one restriction, is our calculator doesn't actually ever write the mu. It says x bar, but that is your population mean. So for this example so far, the average number of girls in a family is 2. And we expect most families to be away from that by 1 on average. Maybe they have 1 more girl or 1 less. It could be further away, but typical families have 2 girls, families of 4, have 2 girls with maybe 1 more or 1 less. Questions? Kevin and Brian, are you guys good? Or you have a question for me?
Yeah, it's just his calculator's a little tricky.
The calculator's grouchy?
Yeah, I don't know what's going on with it.
Let's see. What do we got?
His tape is all good, right?
Let's check your tape. Let's see if you did L1.
Box and medium.
Check that. So when you do one dark stat, make sure you do L1, L2. Because you have to tell them the probabilities too. Now it enters. Yeah, now your calculator's not grouchy.
You just look at X bar
That was like
for the
freshman year.
population.
Yes.
Yeah. But if I go too deep, it's too big. I think it's just because I'm used to this now. Yeah.
It's right But his, he doesn't have a screen, so he has to put the.
Oh wait, with the variance.
Yes, it still works. Yours actually matches my directions better. Okay, before we all lose focus, maybe it's too late. So now that we're getting our calculators figured out, Christian had a really good question. You will be asked for the population mean, which is mu, but the calculator will call it x bar, which we know is really the sample mean. So even though we want mu, the calculator calls it x bar, but that is our mu when we're doing probability distribution. Questions about mu versus x bar? The reason we had to care about that in chapter 3. And what if I wanted the variance? What's variance? Who remembers that? Close. Before you round it? What's the symbol?
I know before you.
Okay, but we're not square rooted here. Our calculator did it. What's the symbol for variance? Something squared.
I think it's like the.
Yeah, it's sigma squared. Sigma squared was the variance. Someday you might want to go back and review your chapter 1 through 3 test. Because everything in there is going to keep coming back. Sorry, what did you ask me, Jenna?
Oh, no, that's just
So in this case, it's 1 squared, because we already have the answer for it. You will never see the variance on your screen. You have to take your standard deviation and square it. You had to do this back in chapter 3. You just chose to forget it all. So in this case, it's also 1. This is the population variance. So I will never refer to those formulas asking you to find the population mean, standard deviation, or variance. I'm going to assume that you can use your calculator. If you're doing these problems online on MyStatLab and you say, help me solve this, it's going to tell you to use the formula. It doesn't know that you have the fabulous calculator. So make sure you're putting really good notes in your notes that you're taking right now, saying, hey, I can always do this on a calculator. Can you not read it, Kirsty? I see you squinting over here.
I'm waiting for my glasses to come, so I'm like,
Oh, no.
disadvantage at them.
Questions here? Think we're good there? Okay, at the bottom of the page, can you turn the other lights back on there, please? Thank you. I think we're about to do more calculators, so I'm going to leave this on for the moment. But the round-off rule hasn't really changed. We didn't have to round this at all, actually, because they were whole numbers. And again, I'll tell you where I want you to round. Tell me what you want me to read to you, Kirsty.
Oh, no, I just got it.
You got it? Okay. If you can't read it, then just let me know. And then see where it says unusual at the bottom of the page? We've been crossing off the word unusual all semester long. What have we been replacing it with? Significantly low or significantly high. Bottom of page 56. Cross off the word unusual and change it to significantly high or significantly low. And do we agree that's the same definitions we've been using all semester? More than 2 standard deviations away from the mean? So we would do 2 steps below or 2 steps above and see if we were further away? So this part hasn't changed. There's another way we can tell if something is significantly high or low. It's not written here. It's if your probability is so small that the event is unlikely. For example, I talked before about my coin and I flip 100 times and I get 99 tails. What do you think the probability is that I will get 99 tails out of 100? You can't actually calculate it, but if you had to estimate it.
Unlikely.
Really unlikely. You expect it to be a really tiny probability, maybe 0.000000. It's possible, but highly unlikely. It's so small, it's definitely less than 0.05. So that's unlikely to happen, which means that 99 must be some significantly high number of tails. So significantly high is far enough from what you expect, but also the chances of it happening are really low. We'll talk about that as we go today. Or a low probability. Is 4 a high number of girls to have? Is 4 significantly high?
Yes,
Yeah? Why yes?
that's a lot of girls.
It's a lot of girls.
Close to 5.
Okay, it's not a judgment call, it's a statistical question. Significantly high is more than 2 standard deviations away from the mean.
Yeah. Because it's 2 exactly away from the mean.
So is it more than 2?
No, it's exactly.
Aha. So let's talk about that. The mean was 2. 1 standard deviation away would take me to 3, and another standard deviation would take me to 4. So if they had more than 4 girls, that would be significantly high, and not to mention impossible. But 4 is not significantly high, because it's right on that cutoff. Right on the cutoff. It's not more than 4, it is 4. And what is 1/16 as a decimal? Can someone divide that for me? 0.0625? Is that an unlikely probability? Definition of unlikely
Has to be less than.
has to be less than 0.05, 5% or 0.05. Is this less than 0.05?
No.
So that's not unlikely. So it's not unlikely to have 4 girls, which means 4 must not be significantly high. These words are going to get interchanged a lot. If something is, the whole reason we keep asking you, is this likely or unlikely? Is this so unusual that we say this is really high or really low? So that's not less than 5%. Not less than 0.05. So it's not unlikely. I'm about to pass back the quiz from last time where a lot of you got this part wrong. You said, oh yeah, that is unlikely. It's not more than 2 standard deviations away from the mean, and it doesn't have a probability less than 0.05, so it's not unlikely. I agree it's less likely than some other things, but it's not, if someone says, wow, this family of 4 kids had all girls, you wouldn't be like, wow, that's really strange. Or imagine if they had 10 kids and they were all girls. Then you might be going, you know what? 10 girls is really unlikely. There's a certain number where all of a sudden it seems a little bit more odd, right? Other questions, Comments? We're getting there? Okay. Expected value. Top of page 57. I expect you to highlight, circle, scribble, star, whatever you need to do on the top of page 57. When you're asked for the expected value, what are they really asking for? It says it right there on the page. The mean. The expected number of girls here was 2. We expect a family of 4 girls to have, 4 children to have 2 girls. The mean was 2. The expected value is the mean. I can't say that enough. Sometimes they call it the expected number. Sometimes they'll say, how many of these do you expect? They're asking for the mean. So what's the answer to the question there? What's the expected value for this example? 2. This is the expected value. We agree the mean is the expected value. That's gonna kill us. Let's do example 7, and then we'll take our break, and then we'll do more expected value after the break as we move on. Most of the time when you're asked for expected value, they're not going to hand you your probability distribution the way I did here. You quite often have to create it yourself. You have to create it yourself. Similar to when I was talking about that lottery over here, where I'm like, we're going to win $1 million or we're going to lose $1, whatever it might be. So example 7 says, what's the expected value when we bet $1 to play California's Fantasy 5 lottery, which we talked about last time. We're going to flip back there in a second to talk about it. And the jackpot's $500,000. So they're saying, how much could you expect to win on average? Some people might win the $500,000 jackpot. Some of us are going to lose our dollar from playing. On average, what do we expect to happen? It's kind of like the other one I brought up earlier. So what you need to do when you're asked for expected value is create your own distribution. Create your own distribution. X and P of X. And this is how much I will win. Think of it as your profit. If I play this lottery, what are all the things that might happen? Kind of gave you a clue earlier.
0.
Well, it's not even 0, it's worse than 0.
Well, you lose more.
You lose your dollar,
So
right?
you're going back negative.
So I might lose my dollar. I'm going to put that one second. I might lose my dollar. It doesn't matter if you put it first. I just like to put losing second. Winning feels better. How much would I win?
After taxes, like 200.
No taxes. We live in a perfect world where there's no taxes. I'm hear some of you say 499,999. I'm only going to win that much because I had to pay $1 just to get in the lottery. This is how much I would win. We agree where that came from? Anything else that might happen? Either win or I lose. So now I need probabilities over here. And the reason I referred to example 5 from last time is we actually calculated this probability last time. Someone have to tell me what page that's on. Example 5 is a couple pages back. Let's see if I can find it. Oh, it's just 1 page back, on page 55. Only 1 page back. On page 55, we calculated this probability. If we hadn't already done it, we'd have to do this little probability question separate to get that probability. You see example 5 on the previous page? And we calculated the probability of winning here. We were using combinations. And I think it was 1 out of 57, 57, 57. So we actually did this work earlier. So I'm trying to make my own probability distribution. We didn't calculate the probability of losing though. We only calculated the probability of winning. I might win or I might lose. How can I find this probability right here? I could either subtract this fraction from 1, or I can say, if there's one way out of 57, 57, 57 way to win, how many ways are there to lose? How many ways could I lose? And I hear somebody over here saying it. 5, 7, 5, 7, 5, 6. All of, oops, not one, sorry. I'm trying to say one less. These are all the probability of winning. There was only one way that I could win, and there are almost all the other ways that we could lose. We have to calculate this on our own. That wasn't given to us. Kirsty's idea of taking 1 minus this is the same thing. We'll be doing that after our break. Questions on what I'm doing, where I got my numbers, and like, whatever. Yes.
So if we didn't do the first part of it, like on the previous page, how would we find that?
So if we didn't do this first part already and have it, I would have had to give you all that information from the previous page so that you could calculate it. So sometimes you'll be given that number, the probability, sometimes you might have to calculate it, but you'll be given all the information you need. So I could have put these two problems together, in which case you would have had to calculate this and then find the expected value. Other questions about getting the table, the probabilities? What is the question asking for? Expected value, which tells me I want to use my calculator to find, someone said it over here, the mean. So how am I going to use my calculator? What am I going to do?
List 1, list 2.
List 1 and list 2. Make sure you put your negative in there for your negative 1. I'm going to put mine in here real quick to see if we agree. So we're going to stat. We're going to clear our little list up here. Don't delete, just hit clear. Delete's going to be the issue that I wanted to have back there. Clear. So all I'm going to put in is my 4,999,999. That's all my nines. And my negative 1. Use the negative number down here at the bottom, not the minus sign, you'll get an error. See where my little cursor is there? Negative at the bottom of your calculator. It's different than minus. And then again, you can just type in your fractions over here. 1 divided by 575757. And if I hit enter, it'll turn it to scientific notation because it can't squeeze it in there. And then 575756 divided by that. Look at what it did. Did you guys see that? It put a 1 right there.
Yeah.
What does 1 mean with probabilities?
Likely.
It's even stronger than likely.
It's gonna happen.
It's gonna happen. Do we know we're definitely gonna lose? No, we don't. It's darn close. We can assume we're gonna lose, but you could win. Why does the calculator say it's 1? It can't fit all the digits. It's like 0.9999999 and some change, and it just can't fit them all in that little space. So don't panic if your calculator says 1. It actually is keeping all the digits in its memory, it just can't show them to you. So now what? Can you turn off one light switch again, please? Sorry. Thank you. Now what?
Now you hit stats.
Now we do stats, and we go over to calculate, and we do 1 bar stats. List 1 and list 2 if you have this screen. If not, you type list 1 comma list 2. And you get this. We get that number? Negative 0.1315.
Yep. Is that the number that we use?
That's our mu.
The X bar?
The X bar is your mean, but the calculator calls it X bar. Let me turn it back on now, please, thank you. Well, what the heck does this have to do with the lottery? There will be a question on the exam that asks you to interpret what this means. Just because you can find it is not the important part of this class. The important part of the class is what does this mean? This is the average. A mean is an average. The average winnings. Right? We're finding out how much people win. So on average, how much does everybody win? They lose.
Negative.
That's because it's negative. And how much do they lose? 13 cents. A little dollar sign in front of here, right? They lose. That's not bad.
Only costs 13 cents to get a thrill. Not
Yeah, to get a little thrill. So if you play the lottery over and over and over and over again, and sometimes you win, and then you keep losing and losing and losing. So if we kept playing all the time, because that's our thrill, right? On average, you take your winnings and your losings, and on average, it's like you're losing 13 cents every time. Even though some people got paid $500,000, the rest of us had our thrill and got nothing, right? On average, we're all losing 13 cents.
That's not bad then if you think about it.
It's not bad, really. Think about what the state gets, though. Every time somebody buys a ticket, whether that person wins or loses, the state gets to keep that 13 cents. So essentially, everybody who plays the lottery is handing the state 13 cents. Here's my 13 cents, here's my 13 cents. Even though you might be the winner or the loser in the long run, on average, they're getting 13 cents from each person. The state earns 13 cents from each ticket.
It doesn't seem like much, but I've worked at a gas station before, and there's a lot of people who play the lottery.
Oh yeah, imagine that 500,000 people buy tickets. 500,000 times 13 cents isn't just, I mean, and it's probably more like millions. There's some people who buy 20 tickets at a time.
Isn't it a weekly thing too?
Yeah, so I think sometimes it's twice a week even. Like it used to be Wednesdays and Sundays, or I don't even
They're
know.
making a lot of money off of that, 13 cents.
Oh yeah, 13 cents every time. Questions about interpreting that expected value? Okay, let's take a break. We'll come back, we're going to do some more expected value, and then we'll move on and talk some more about a specific probability distribution. I'll see you in 10 minutes. So now that we all realize that we are losing the lottery every time we play,
California's getting rich off of us.
California's getting rich off of us as we all lose when we play the lottery. By the way, I don't ever play the lottery because I'm a statistician and I understand how it works.
As much as I wanted to win that $1 million.
I have, you know, bought like scratch-offs, put in stockings for people. Those are gifts as opposed to trying to win, right? So example 8 is another expected value question, and it kind of goes back to what Carrie was asking earlier. We have to figure out the probability. It's not like it's referring to an earlier problem. So looking at example 8, now we're going to the casino and we're playing roulette. We've given up on the lottery. Now we're going to go try to see, try our luck at the casino. We're playing roulette. And there's 38 spaces. Even if you've never been to a casino, you've probably seen a roulette thing on TV or a movie, right? You spin the wheel and the little ball bounces around and has to land in a specific little spot, right? There's actually a lot of different ways you can bet. But there's, according to this, there are 38 little spaces for that little ball to spin around and bounce into. 38 spaces. 18 of them are white, 18 of them are black, and 2 of them are green. They have numbers on them and stuff too, but we're not worried about that right now. And we're going to bet $5 on black. So we're going to go to the casino, we're going to bet $5 that that little ball is going to bounce around and end up in the black square. And if we do, we're going to win $10. Sweet. Double our money, just like that. We want to know what is your expected value when you play this game just once. What can you expect to win when you play roulette once and you bet on black? What should I do? I should make a table. Anytime they're asking for expected value, I should make a table. Okay, I should make a table. What goes in my table?
X is the number of outcomes.
X is not the number of outcomes, but what the outcomes could be. So,
Like events or?
like the events, like what would happen if I play this game? I might win or I might lose, right? Yeah, it's either going to be black or it's not going to be black, right? But either, think of it again as how much I'm going to win, or my profit, just like we talked about before. So I might lose my $5, right? If it doesn't come up black.
You might break even.
Can I break even? I don't know if I can break even. What's it say is going to happen? Can you pull that door shut, please?
But you can make $10.
So I would win $10, but am I making $10? Be careful.
No, you're winning 5.
I'm only winning 5. this is if I lose. Well, let me just even be more specific. If it's not black, I lose my $5. Right? We agree with that? But if it does come up black, even though they're paying me $10, I paid $5 to play. So do you agree I'm only winning 5? It's always about your profit, not how much they'll hand you, but how much you walked away with that you didn't have to begin with. So if I walk in there, I give them 5, and I walked away with 10, I really only won 5. We agree those are the two things that could happen? So now I need some probabilities. And I'm actually really glad that I wrote not black and black right here. Let's do the black one first. What is the probability on this wheel that the little ball lands in a black space? 18 out of 38, she says. What did you say, Kevin? Were you saying the same thing?
I didn't say anything.
Oh, I thought I heard somebody say something back there. No?
Wouldn't it be 50%?
Ah, we wish. They want you to think it's 50%. 50-50? If there only were black and white spaces, I would agree with you, but they threw in those 2 green ones.
That's right.
So if there were 36, 18 black and 18 white, I'd totally agree with you, it'd be 50%. But because those darn green ones are in there, there's only 18 out of 38 that are black. How many of them are not black? 20 out of 38. So they want you to think it's 50-50, which is why everyone keeps playing. But there's actually a little bit more chance that you'll lose than there is that you'll win. Slightly more than 50%. We agree with that? It's a little bit more than half, it's a little bit less than half. So we've created our table, and we want to know what the expected value is. What should I do? Put it in the calculator and find the mean. See if we can all punch that in there correctly. Clicking noises have quieted down. I mean, most of us are there. Type in list 1, list 2. One bar stats with list 1 and list 2. What did we get? It says X bar on your calculator, but it's our population mean.
It's like negative 263, and then there's a bunch of numbers.
Negative 263? Is it round to 63 or 64?
0.263.
Oh, 0.263?
Yeah.
Oh. So 0.26 if I'm talking money. I'll round it to the cents place if I'm doing money, right? 0.26? What does that mean every time we go to the roulette table to try to win? We're losing 26 cents every time we play. Even though sometimes it comes out black and they give you $5. 5 extra bucks. They give you 10, but it's 5 extra. If you keep doing it over and over, every time you play, on average, you're losing 26 cents. You ever been to a casino? They've got free drinks, they've got all these lights and sounds and all this cool stuff. Guess who pays for it all?
We do.
We do. 26 cents every time the roulette thing goes around. And that's if you bet only $5. People that bet a heck of a lot more than $5 are giving them even more. If you bet $50, you're multiplying that by 10, right? You're losing a lot of money. Casinos aren't paying for any of that. We all are. They're not really free drinks. And they're watered down, too.
It's cheap alcohol.
Cheap alcohol, yeah. Cheap alcohol, less
You're really
alcohol.
losing all the way.
And we're paying for it. Other than that, it's a great time. Questions on that? Yes.
So if you threw another variable into that, like say you chose black, but you put like a number on black, like black 17, how would you calculate the probability?
Okay, so let's say you wanted to pick a specific number.
Sure.
So let's say he wanted to be the 17, which happens to be black. There's only one black 17 out of the 38. So your probability would have been 1 out of 38.
Would it have been 30?
Oh, yeah.
And because there's 38 spaces, and then the probability of losing would have been 37 out of the 38. Either you win or you lose. Actually, I have it backwards.
So the green one still matters?
Well, they're in my 38.
Oh, I thought it was 36 and then.
It's 38.
1 out of 38.
1 out of 38 would be your probability of winning. And then obviously there would be a 37 out of 38 because all of the other ones would not be your black 17. And the difference is to make you want to try this, the payoff is much higher for this. Like if you bet $5, I don't know what the payoff is. The payoff might be $100, but it's still not enough for you to come out ahead in the long run. So the more unlikely of the event, the smaller the probability, the more the casino pays you. Because it's hard to pick the exact one it's going to go into. So if you do, they're going to give you a lot of money. But they know the chances are so slim. And having those 2 extra green ones are what do it. They essentially ignore the green ones when they figure out how much they're going to pay you, and know that every time it lands in the green ones, they win.
You can't bet green, can you?
I think you can, and the probability is, again, really small.
Right.
And so again, but the payoff's not enough that the expected value would come out positive for you ever. The casinos don't ever set it up in a way that you will come out ahead of them. We could spend hours, days talking about all the different ways they set their probabilities and how it's so close to being 50-50, like you said, but just off enough to make it so it's in their favor. Yes.
It was the one time I went to the casino and the person next to me won $1 million.
Yeah. So somebody next to her won $1 million at the casino. We're not saying people don't win, but guess who paid for that person's $1 million? The rest of us. We all lost, and on average, and then that person. So that person thinks, wow, this is a deal. I can get rich. But if that person keeps going back over and over again and reinvesting their $1 million in the long run, they're losing every time. When you go up ahead, then you end up down at the end. It's quite sad. That's why people have gambling problems. But speaking of other options, there is, I think, at least one homework problem where you need to make a table like this where there are more than one thing that could happen. Like if you entered a contest where maybe you'll win $50 or maybe you'll win $100 or maybe you'll win the grand prize of $500, you might have more options here. Like maybe you could win, let's say it was free, let's say we paid $1 to get in. So you might win 50 or you might win 100, so that'd be 99. These are your profit if you paid $1 to join in. These are all the winnings. Maybe you have more than one, or maybe you could win $1,000, which means really $9.99, or you lose your $1. Maybe these are all the things that could happen. You win $50, or you win $100, or maybe you could even win $1,000, or maybe you lose your $1 for entering.
So
It's
you always-
possible.
You
Yes.
always have to subtract the 1 from what you paid.
Exactly. You always have to subtract the 1, consider there is the option that you might lose. And they might tell you, well, the chances of you winning this $50 is 1 in 100. They might give you that probability. They even actually say that on the back of some sweepstakes forms where they tell you the probabilities of winning the certain things. And the chances of winning the $100 is 1 in 1,000. And the chances of this is 1 in 10,000. I'm making these up as I go. Oops, maybe it's 100,000. I put an extra 0 on there. So they might give you those probabilities. But they don't give you this one. Could we find it?
Yeah.
Could we find that one if we don't have it? You'll be asked to do this. Sorry, what was saying?
Don't they just equal to 1?
They have to add up to 1, remember? So how can I find what goes here?
And you subtract it like you did before.
Exactly. Add all these up, get whatever that is, and subtract it from 1 to see what's left. This number that goes in here will be 1 minus whatever those add up to, which I'm not going to do the whole problem right now. I just want to give you a heads up because you're going to see one on your homework. We agree that if I add those all up and subtract it from 1, I can see what goes in there? And then I can find the mean and go from there. So sometimes there are more than one possible way you could win. There's still a lot more chances that you're going to lose. Everyone all right with that little heads up? Questions? What's the expected value? Mean, thank you. The mean is the expected value is the mean.